linear algebra, matrices, and system of linear equations. At the end of this topic, we should be able to transform a system of linear equations into a matrix form and find the solution for the system of linear equations using Gaussian elimination. First, what is a system of linear equations? A linear equation with n variables x1, x2 until xn is represented as follow, where an and b are constants, and an is called as leading coefficient, where xn is called as leading variable. This system will have a solution of real numbers where x1 equal to x1, x2 equals to s2 until xn equals to sn. Consider this system of linear equations. The matrix form of this system of linear equation is represented as ax equals to b, where a is called as coefficient matrix, x is called as variable matrix, and b is called as constant matrix. Let's see some example. Consider a system of linear equations which consists of two variables x and y. The matrix form of this system is ax equals to b, where the element in matrix A is the coefficient of x and y. This one is the variable x and y, and this matrix is 5 and negative 2, which is constant. Solution for this system is x equals to 1 and y equals to 0, which is unique solution. For the second example, consider a system of linear equations of three variables x, y, z in matrix form represented as follows. Unlike example 1, the matrix in example 2 is a non-squared matrix. The solution for this system is given as follow, and this system has many solutions. This T is any real number. For a system of linear equation or for matrix, there are three types of solution: unique, many, and no solution. So consider these 7 examples. So first step, to decide the type of solution of a system, first step you have to mark the leading one. For example 1, there are 2 leading one. For example 2, there are 3 leading one. For example 3, there are 2 leading one. For example 4, there are 3 leading one. For example 5, there are 2 leading one. For example 6, there is 1 leading one. And for example 7, there are 2 leading one. And then mark a column without leading one. Example 1 and example 2 do not have columns without leading one. Example 3 have 1 column without leading one. Example 4 has 1 column without leading one. Example 5 has 2 columns without leading one. Example 6, 1 column without leading one. And example 7 has 2 columns without leading one. So based on the information of leading one and also the column without leading one, we can decide the type of solution. For example 1, there are 2 columns in the matrix and there are 2 leading one. Therefore, this system will give unique solution. Similarly, for example 2, since there is 3 columns in the system and 3 number of leading one, therefore this system will also have unique solution. For example 3, since there are 3 columns and 1 column has no leading one, therefore this system has many solutions, and since it has 1 free variable, we can also call this system as 1 parameter solution. Similarly, for example 4, since there is 1 column without leading one, this system has many solutions, and has one free variable. Therefore, we can call this system as many solution and one parameter solution. For example 5, there are two columns with a leading one. Therefore, this system will have two free variables. The solution for this system is many solution and two parameter solution. For number 6, although there is one column without leading one, but the last row suggests that this system is inconsistent. Therefore, it has no solution. For number 7, similar to number 5, there are two columns without leading one. Therefore, this system has many solutions, and this system is a two-parameter solution. How to solve a system of linear equation? There are several techniques to solve a system of linear equation, such as inverse, Cramer's rule, Gauss elimination, and also Gauss-Jordan. However, in this subtopic, we will discuss only Gauss elimination and Gauss-Jordan elimination. For Gauss elimination, we will use elementary row operations. There are three standard elementary row operations as given in this table. The first one is by interchanging between two rows. The second one is by multiplying a row with a non-zero constant. And the last one by adding a row which is multiplied with a non-zero constant to another row. Consider these two examples. The first one, given the following system of linear equations, determine the value of alpha and beta such that the system has unique solution, no solution, or one parameter solution. The augmented matrix form of this system is given as follows. Reduce the system to the row echelon form. So we can decide the type of solution based on the relation on the last row. For unique solution, it happens when beta does not equal to 0 and 1 minus alpha is any real number, where alpha is also any real number. For question B, no solution, it happens when beta equals to 0 and 1 minus alpha does not equal to 0, which suggests that alpha does not equal to 1. For one parameter solution, it happens when beta equals to 0 and 1 minus alpha does not equal to 0, which suggests alpha is equal to 1. For second example, there are two types of equation. The first one, consider this matrix A as homogeneous system of linear equation, and number two, consider A as augmented matrix. For the first one, A is homogeneous system of linear equations. So find alpha and beta, which the system has one parameter solution and two parameter solution. Homogeneous system of linear equation means that matrix B is a zero matrix. Reduce the system. One parameter solution happens when one of the column has no leading one. But by considering this matrix, when beta equals to 2, two columns will not have leading one. Or when alpha equal to 0, these two columns will not have leading one. Therefore, it is impossible for the system to only have one parameter solution. For two parameter solution, there are two cases. First one, when alpha equal to 0, therefore these two columns will not have leading one, or when beta equals to 2, where these two columns will not have leading one. Question B, A is an augmented matrix, therefore the last column is considered as matrix B. Unique solution, It happens when beta minus 2 does not equals to 0. It suggests that beta does not equals to 2. And alpha cannot be 0. And number 2, inconsistent, which also means that the system has no solution. This case will not happen since if beta minus 2 equal to 0, on the right hand side, it will also equals to 0, which always give many solution.